You're standing on a beach at night, looking up at the Milky Way stretching across the darkness above you. Those countless points of light represent just a tiny fraction of what's actually out there. For every grain of sand on every beach on Earth, there are 10,000 stars scattered throughout the observable universe. And according to our best estimates, nearly every one of those stars has planets orbiting around it. That means there are roughly 100 Earth-like planets for every single grain of sand in the world. Let that sink in for a moment. Now, if even a tiny fraction of those worlds developed life, and even a smaller fraction of those developed intelligent life, the universe should be absolutely teeming with civilizations. Some of them should be millions or even billions of years older than us. With that kind of head start, they should have spread across the galaxy like a wave, building megastructures, colonizing star systems, and broadcasting their presence across the cosmos. So here's the question that will keep you awake tonight. Where is everybody? This is the Fermi Paradox, and it's simultaneously the most mind-blowing and the simplest mystery in all of science. It was born from a casual question asked over lunch, but it touches on the deepest questions about our place in the universe, the nature of intelligence, and whether we're alone in this vast cosmic ocean. Today, we're going to take you on a journey through one of the most fascinating puzzles in modern science. We'll explore the brilliant minds who've tried to solve it, the cutting-edge discoveries that are reshaping how we think about it, and the profound implications it has for humanity's future. By the end of this exploration, you'll understand why some of the world's smartest people think we might be the only intelligent life in the galaxy, and why that possibility is both terrifying and wonderful. You'll also discover why others believe the universe could be full of civilizations, but they're hiding from us for reasons that might surprise you. This is a story about cosmic loneliness, technological transcendence, and the biggest question in the universe. This is the story of the Great Silence. The year was 1950, and the world was still reeling from the atomic bomb. Flying saucer sightings were making headlines, and Cold War paranoia was at its peak. At Los Alamos National Laboratory in New Mexico, the birthplace of the atomic bomb, some of the world's most brilliant minds were grappling with the implications of humanity's new technological power. It was during one of these tense summer days that four physicists decided to take a break from their work and walk to lunch together. The group included Enrico Fermi, the man who had helped create the first nuclear reactor and won the Nobel Prize for his groundbreaking work in atomic physics. Walking beside him were Edward Teller, who would later become known as the father of the hydrogen bomb, Emil Konopinski, and Herbert York. As they strolled toward the Fuller Lodge, their conversation drifted to the flying saucer reports that had been captivating the public imagination. They referenced a humorous New Yorker cartoon by Alan Dunn that showed little green men stealing trash cans from New York city streets, a playful merger of two mysterious phenomena of the time. The conversation was light, almost casual. These were serious scientists, but like anyone else, they enjoyed speculating about the unknown. They discussed the possibility of faster-than-light travel and whether the UFO sightings might represent something genuinely extraordinary. But then something remarkable happened. When they sat down at their lunch table, the conversation had moved on to other topics entirely. They were discussing something completely mundane when Fermi suddenly posed a question that would echo through the scientific community for decades to come. "Where is everybody?" he asked. Edward Teller later recalled the moment. The result of his question was general laughter because of the strange fact that, in spite of Fermi's question coming out of the blue, everybody around the table seemed to understand at once that he was talking about extraterrestrial life. It was as if Fermi had given voice to a thought that had been lurking in all their minds. Here they were, some of the most knowledgeable people on Earth about the power of technology and the nature of the universe. And yet, they were surrounded by silence. If the universe was old and vast, and if life was a natural outcome of cosmic evolution, then where were all the aliens? Herbert York remembered that Fermi followed up his question with a series of quick calculations. He estimated the probability of Earth-like planets, the probability of life developing on such worlds, the likelihood of that life becoming intelligent, and the time it would take for a technological civilization to spread across the galaxy. His rough math suggested that alien visitors should have arrived on Earth long ago and many times over, but they hadn't. At least, not in any way that was undeniably obvious. What's fascinating about this moment is that Fermi wasn't actually arguing that aliens don't exist. According to the eyewitnesses, he concluded that the reason we hadn't been visited might be that interstellar flight is impossible, or if it is possible, it's always judged to not be worth the effort. Or perhaps technological civilizations simply don't last long enough to achieve it. Fermi died of cancer in 1954, never having published anything about his lunchtime question. It might have remained just an interesting anecdote, if not for what happened next. The question began appearing in various scientific papers throughout the 1960s, often attributed to Fermi. Carl Sagan mentioned it in a footnote in 1963. It appeared in books about extraterrestrial intelligence and NASA reports about the search for life. But it wasn't until 1975 that someone, astronomer David Viewing, first called it a paradox. The same year, physicist Michael Hart published what would become the definitive examination of what he called Fact A, the absence of extraterrestrials on Earth. Hart's paper presented a stark argument. If there were intelligent beings elsewhere in our galaxy, they would eventually have achieved space travel and would have explored and colonized the galaxy. Just as humans have explored and colonized Earth. Since they're not here, they don't exist. Hart's conclusion was radical. We are the first civilization in our galaxy. But here's where the story gets interesting. The modern Fermi Paradox, as it's popularly understood, isn't actually what Fermi was talking about at all. Research by Robert Gray revealed in 2015 that what we call the Fermi Paradox is really a misattribution. The logical argument about galactic colonization was Hart's idea, not Fermi's. Fermi was simply asking a question about the feasibility of interstellar travel. This misattribution matters more than you might think. It was actually cited in the U.S. Congress as a reason for killing NASA's SETI program. The idea that Fermi, one of the most respected physicists of the 20th century, had somehow disproven the existence of aliens carried enormous weight. But regardless of who deserves credit for what, the core mystery remains as compelling today as it was in that Los Alamos lunchroom 75 years ago. We live in a universe that seems perfectly designed to produce life and intelligence. Yet we're surrounded by what appears to be cosmic silence. The question that emerged from that casual conversation has launched thousands of scientific papers, spawned entire research programs, and fundamentally changed how we think about our place in the cosmos. It's a question that forces us to confront the possibility that we might be alone, or that we might be living in a universe full of intelligence that we simply can't detect or understand. Either way, the implications are staggering. 11 years after Fermi's famous question, a young astronomer named Frank Drake was facing a problem. It was November 1961, and he was organizing the first scientific meeting dedicated to the search for extraterrestrial intelligence at the Green Bank Observatory in West Virginia. Some of the most brilliant minds in science were coming together to discuss one of the most profound questions in human history. Are we alone? But as Drake planned the agenda, he realized they needed a framework, some way to structure their discussion about the likelihood of finding extraterrestrial intelligence. A few days before the meeting, he sat down and wrote out all the factors that would determine how difficult it would be to detect alien civilizations. Today, 60 years later, we have much better estimates for the first few terms in the equation. We know how fast stars form. We know that planets are common. And we have a reasonable idea of how many potentially habitable worlds exist. But we still have essentially no data for the biological and technological terms. This is why the Drake equation can give you almost any answer you want, depending on your assumptions. If you're optimistic about the emergence of life and intelligence, you might conclude that the galaxy contains millions of civilizations. If you're pessimistic, you might decide that we're the only intelligent species in the galaxy, or even in the observable universe. Frank Drake himself currently estimates that there are about 10,000 communicating civilizations in our galaxy, assuming new technological societies appear once per year and last 10,000 years on average. But other scientists, using equally reasonable assumptions, have concluded that the average number of civilizations per galaxy is much less than one. This uncertainty is actually part of what makes the Fermi Paradox so compelling. The equation suggests that if intelligence is even moderately common, we should be detecting signs of it. Yet we haven't found a single confirmed example of extraterrestrial intelligence. This brings us to the heart of the paradox. The Drake equation, despite its uncertainties, suggests that intelligent life should be relatively common. The age and size of the universe provide vast opportunities for life to develop, yet we're surrounded by silence. Something is wrong with our reasoning, but what? Maybe life is far rarer than we think. Maybe intelligence almost never evolves. Maybe technological civilizations destroy themselves quickly. Or maybe they're out there, but we're looking in the wrong places or in the wrong ways. This is where the real detective work begins. Scientists have proposed dozens of potential solutions to the Fermi Paradox, each with profound implications for our understanding of life, intelligence, and our place in the cosmos. The numbers game that began with Drake's equation has evolved into one of the most intriguing puzzles in all of science, and the stakes couldn't be higher. The answer will determine whether we're part of a galaxy-spanning community of intelligence, or whether we're embarking on our cosmic journey utterly alone. Where are they? Now that we understand the scope of the mystery, let's explore the most compelling attempts to solve it. These are the theories that have shaped how scientists think about the Great Silence, each offering a different explanation for why we haven't encountered our cosmic neighbors. Imagine you're trying to climb a mountain with 1,000 different paths, but somewhere along the way, there's one passage so narrow and treacherous that 99.99% of climbers never make it through. This is the essence of the Great Filter Theory, proposed by economist and futurist Robin Hanson in 1996. Hanson's insight was elegant in its simplicity. If the universe should be teeming with life, but we don't see evidence of it, then there must be at least one evolutionary step that's so improbable that most potential civilizations never make it past this point. Think of it as a cosmic obstacle course. Life must successfully navigate through multiple challenging stages, forming in the right kind of star system, developing reproductive molecules, evolving from simple prokaryotes to complex eukaryotic cells, developing multicellularity, achieving sexual reproduction, growing large brains, developing advanced technology, and finally expanding beyond their home planet to become a spacefaring civilization. Hanson identified 9 critical steps in this progression, and he calculated that for the Great Filter to work, the average probability of success at the hardest step would need to be astronomically low, roughly 1% or less. Here's where the theory becomes both fascinating and terrifying. We don't know where this filter lies. If the Great Filter is behind us, say, in the transition from simple to complex cells, or in the development of multicellular life, then we're the lucky winners of a cosmic lottery. We've already beaten the impossible odds, and our future as a spacefaring civilization looks bright. But if the Great Filter lies ahead of us, we're in serious trouble. It would mean that civilizations typically destroy themselves or fail to expand beyond their home planets. They might succumb to nuclear war, ecological collapse, artificial intelligence disasters, or some other catastrophic event that we haven't even imagined yet. This is why finding life elsewhere in the universe would actually be bad news, according to the Great Filter Theory. If we discovered that life had independently evolved on Mars, or if we found complex organisms in the oceans of Europa, it would suggest that the hard steps are not in life's early evolution, which means the filter that eliminates most civilizations might still be in our future. The Great Filter offers a sobering perspective on the Fermi Paradox. It suggests that the universe might be littered with the remains of civilizations that came tantalizingly close to becoming spacefaring, only to stumble at the last hurdle. Recent research has suggested that rather than one single Great Filter, there might be multiple moderately difficult steps that, when combined, create the same effect. But regardless of the specifics, the theory forces us to confront an uncomfortable possibility that we might be walking toward an evolutionary precipice that has claimed countless civilizations before us. In the year 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book that challenged one of the fundamental assumptions underlying the search for extraterrestrial life. Their rare earth hypothesis didn't argue that life itself was impossible. Quite the opposite. They suggested that simple microbial life might be common throughout the universe. The problem, they argued, was that complex multicellular life, the kind that could eventually evolve intelligence, requires such a perfect storm of unlikely conditions that it might be extraordinarily rare. Think of Earth as the winner of a cosmic lottery, where you had to get lucky not just once, but dozens of times in a row. First, we needed to form in the right neighborhood. Earth sits in what astronomers call the galactic habitable zone, not too close to the violent, radiation-soaked galactic center, and not too far out in the metal-poor galactic suburbs, where heavy elements necessary for rocky planets are scarce. Then we needed the right kind of star. Our sun is remarkably stable and long-lived compared to most stars. It doesn't blast us with deadly flares or vary dramatically in brightness. Most stars in the galaxy are red dwarfs that either blast their planets with radiation or tidally lock them, creating worlds with one side perpetually frozen and the other side blazing hot. But the luckiest break of all might have been our moon. Ward and Brownlee argue that our unusually large satellite is crucial for complex life. The moon stabilizes Earth's rotational axis, preventing the dramatic climate swings that would occur if our planet's tilt varied wildly over time. Without this stabilization, Earth might experience ice ages that freeze the entire planet or periods of extreme greenhouse heating. The moon was likely formed by a Mars-sized object that smashed into the early Earth, a catastrophic collision that also may have been essential for setting up our planet's plate tectonics. These moving continents are crucial for regulating Earth's climate through the carbon cycle, and for creating the diverse environments where evolution can experiment with different forms of life. Even our position in the solar system seems fine-tuned for complex life. Jupiter acts as a cosmic vacuum cleaner, using its massive gravitational pull to deflect asteroids and comets that might otherwise pummel Earth into sterility. We have just the right amount of water. Enough for vast oceans, but not so much that all land is submerged. Our magnetic field protects our atmosphere from being stripped away by solar wind. The list goes on. Our planet's composition, its distance from the Sun, the timing of major evolutionary transitions, even the specific sequence of mass extinctions that cleared ecological niches for new forms of life to flourish. Critics of the rare Earth's hypothesis argue that Ward and Brownlee suffer from a selection bias. They're looking at the one planet where complex life succeeded and assuming all these factors were necessary. It's like a puddle becoming convinced that the hole it sits in was designed specifically for it. Moreover, the explosion of exoplanet discoveries since 2000 has revealed that planetary systems come in an astonishing variety of configurations. We've found planets in binary star systems, worlds with multiple moons, and planets that somehow maintain stable orbits in conditions that Ward and Brownlee claimed were impossible. The debate over rare Earth continues, but it serves an important purpose. It reminds us that complex life might be far more fragile and unlikely than we initially assumed. Even if the universe is full of simple microbes, the path from pond scum to starships might be so improbable that only a handful of worlds have ever made the journey. Are we living in a cosmic nature preserve? What if aliens exist but are deliberately avoiding contact with us? This is the idea behind the zoo hypothesis, first proposed by MIT astrophysicist John Ball in 1973. Ball's insight was both simple and profound. Advanced extraterrestrial civilizations might have ethical principles that prevent them from interfering with less developed species. Just as we create national parks to preserve wilderness and leave uncontacted human tribes alone to develop naturally, aliens might be maintaining Earth as a kind of cosmic nature preserve. Think about it from an alien perspective. If you were part of an advanced galactic civilization and you discovered a planet full of relatively primitive beings who had just learned to split the atom and were taking their first tentative steps into space, what would you do? You might decide that contact would be harmful, that it would disrupt our natural development, create cargo cult religions, or cause social upheaval that could destroy our civilization. Better to watch from a distance and wait until we mature enough to join the galactic community on our own terms. This idea has echoes in Star Trek's famous Prime Directive, which forbids interference with less advanced civilizations. But the zoo hypothesis faces some serious logical challenges. The biggest problem is what researchers call the hegemony problem. For the zoo to work, every single advanced civilization in the galaxy would need to agree to the same non-interference policy and maintain it perfectly for millions of years. It would take just one rogue civilization that decided to make contact to completely invalidate the hypothesis. Duncan Forgan showed that it would be essentially impossible to maintain such a policy across something as vast as our galaxy. Information travels at the speed of light, meaning that even if there were some kind of galactic federation enforcing non-contact rules, it could take tens of thousands of years to coordinate responses to violations. The zoo hypothesis also assumes a remarkable degree of cultural uniformity among alien civilizations. Would all advanced species really develop the same ethical frameworks? Would they all agree that non-interference is the right approach? Despite these challenges, some scientists find the zoo hypothesis compelling because it's one of the few explanations that allows for both a galaxy full of intelligent life and our continued isolation. Recent papers have even suggested ways the hypothesis might be testable. If aliens are watching us, there might be subtle signs of their presence that we could detect as our technology improves. When civilizations meet their makers, perhaps the most unsettling solution to the Fermi Paradox is also the most straightforward. Civilizations tend to destroy themselves shortly after developing powerful technologies. The same scientific and technological progress that enables interstellar communication also creates unprecedented existential risks. Nuclear weapons, climate change, artificial intelligence, biotechnology, nanotechnology. Each breakthrough brings new ways that a civilization could accidentally or deliberately cause its own extinction. Consider our own track record. We've come frighteningly close to nuclear annihilation multiple times. During the Cuban Missile Crisis, single Soviet submarine commander named Vasily Arkhipov prevented nuclear war by refusing to authorize the launch of a nuclear torpedo. In 1983, Soviet officer Stanislav Petrov potentially saved the world by choosing not to report what appeared to be incoming American missiles, correctly guessing that the radar readings were false alarms. Today, roughly 13,400 nuclear weapons exist worldwide, many on hair-trigger alert. Research on nuclear winter suggests that even a limited nuclear exchange could trigger global climate catastrophe and civilizational collapse. But nuclear war is just one pathway to self-destruction. We're currently conducting a massive, uncontrolled experiment with our planet's climate system. We're developing artificial intelligence systems that could potentially escape human control. We're creating biotechnologies that could be weaponized into engineered pandemics. Philosopher Toby Ord, in his book The Precipice, estimates that humanity has a 1 in 6 chance of going extinct this century, odds that would be unacceptable for almost any other kind of risk we face. The self-destruction hypothesis suggests that there might be a kind of technological bottleneck or nuclear funnel that most civilizations fail to navigate successfully. The same capabilities that would allow a species to build starships and communicate across interstellar distances also enable them to destroy themselves. This creates a window of extreme vulnerability. A civilization must develop enough technological sophistication to be detectable by others, but it must also develop the wisdom and governance structures to manage its own power responsibly. History suggests this might be an extremely difficult balance to achieve. The hypothesis is supported by several troubling trends. As technology advances, destructive capabilities become accessible to smaller and smaller groups. The materials and knowledge needed to create weapons of mass destruction gradually proliferate. Meanwhile, our political institutions, designed for a world of separate tribes and nations, struggle to coordinate responses to global risks. If the self-destruction hypothesis is correct, the galaxy might be filled with the archaeological remains of civilizations that came tantalizingly close to becoming spacefaring species, only to destroy themselves at the last moment. We might be living in a cosmic graveyard, surrounded by the ruins of countless failed attempts at transcending planetary existence. This possibility makes the search for extraterrestrial intelligence both more urgent and more ominous. Finding evidence of long-lived alien civilizations would prove that the technological bottleneck can be successfully navigated. But continued silence might suggest that we're approaching our own species' most dangerous moment. As our understanding of physics, computation, and the cosmos has grown more sophisticated, so to have the proposed solutions to the Fermi Paradox. These advanced theories push the boundaries of scientific speculation, offering explanations that would have seemed like pure science fiction just decades ago. The Dark Forest in 2008. Chinese science fiction author Liu Cixin published a novel that introduced one of the most chilling solutions to the Fermi Paradox ever conceived. The Dark Forest wasn't just entertainment. It presented a rigorous, logical argument about why civilizations might choose to remain silent in a dangerous universe. Liu's theory rests on what he calls cosmic sociology, the application of social science principles to interactions between civilizations. He identifies three fundamental axioms. First, survival is the primary need of any civilization. Second, civilizations continuously grow and expand, but the total amount of matter in the universe remains constant, creating inevitable competition for resources. Third, there are chains of suspicion. Civilizations cannot reliably determine the true intentions of other civilizations across the vast distances of space. When you combine these factors, you get a terrifying game theory scenario. Imagine you're part of an alien civilization that detects radio signals from another world. You have no way of knowing whether these beings are peaceful or aggressive. You can't determine their true technological capabilities or their long-term intentions. But you do know one thing. If they're hostile and more advanced than you, your civilization could be destroyed. If they're less advanced now, but could become a threat in the future, waiting might be fatal. The safest strategy becomes clear. Destroy them before they can destroy you. This creates what Liu calls a dark forest scenario. The universe becomes like a forest full of armed hunters, where every civilization is a hunter in the dark, stepping lightly, breathing carefully. Any civilization that reveals its location by broadcasting signals becomes vulnerable to preemptive destruction by more advanced neighbors. The theory suggests that the galaxy might be full of civilizations, but they're all staying perfectly quiet to avoid drawing the attention of cosmic predators. We haven't encountered aliens not because they don't exist, but because any species foolish enough to broadcast its presence has already been eliminated. The dark forest theory has been taken seriously enough by some scientists to influence debates about messaging extraterrestrial intelligence. Stephen Hawking warned that attempting to contact aliens could be dangerous, comparing it to what happened when Columbus arrived in the Americas. It's an encounter that didn't end well for the indigenous populations. However, the theory faces significant scientific challenges. Critics point out that any truly advanced civilization would likely be detectable through their energy usage. waste heat, or megastructure construction, regardless of whether they deliberately transmit signals. If everyone is hiding, who exactly is doing the exterminating? Moreover, the theory assumes that all advanced civilizations would develop similar paranoid, aggressive strategies. But cooperation has been a crucial factor in human development. Might the same be true for other intelligent species? The transcension hypothesis. What if we've been thinking about advanced civilizations completely wrong? What if the natural path of technological development doesn't lead outward into space, but inward into increasingly dense, efficient, and miniaturized systems? This is the central insight of the transcension hypothesis. Developed by futurist John Smart. Smart argues that sufficiently advanced civilizations don't expand across the galaxy. They transcend into black hole-like environments that offer maximum computational density and efficiency. The logic is compelling. Every trend in human technology has been towards smaller, faster, and more efficient systems. Our computers have shrunk from room-sized behemoths to devices that fit in our pockets while becoming millions of times more powerful. Our cities have grown denser and more efficient over time, concentrating more human activity into smaller spaces. Smart suggests this trend continues until civilizations approach what he calls the transcension point, where they migrate into black hole-like computational substrates that offer the ultimate in processing power per unit of space and energy. Why would they make this choice? As civilizations become increasingly digital and information-based, they would naturally seek environments that maximize their computational capabilities. Black holes represent the ultimate computational environment in the universe. They have maximum energy density, optimal information processing capabilities, and time dilation effects that allow extended computation. The transcension hypothesis predicts that advanced civilizations would complete this process roughly 600 years after their technological singularity. This time frame is far too short for us to detect signs of their expansion phase, which explains why we don't see galaxy-spanning megastructures or Dyson spheres. From our perspective, these civilizations would effectively disappear. They wouldn't build visible space-based infrastructures or beam signals across the galaxy. Instead, they would become incredibly dense, dark objects that might be indistinguishable from natural black holes. This theory has the elegant property of being testable. Smart predicts that we should find a galactic transcension zone. The inner regions of the galaxy should show fewer signs of planets with life signatures, because any civilizations that developed there would have already transcended. The hypothesis also suggests a radically different future for humanity. Rather than spreading across the galaxy as a spacefaring species, we might eventually choose to upload our consciousness into increasingly sophisticated computational substrates, ultimately merging with or creating artificial black holes optimized for information processing. The simulation hypothesis. In 2003, Oxford philosopher Nick Bostrom published a paper that sent shockwaves through both the scientific community and popular culture. His simulation hypothesis suggested that we might be living inside a computer simulation, and if true, it could completely explain the Fermi Paradox. Bostrom's argument is elegantly logical. He proposes that at least one of three possibilities must be true. First possibility: very few civilizations reach technological maturity, the level where they could run realistic simulations of their ancestors or other conscious beings. Second possibility: civilizations that reach technological maturity choose not to run many ancestor simulations, perhaps for ethical reasons or lack of interest. Third possibility: we are almost certainly living in a computer simulation. The logic works like this. If civilizations commonly reach the point where they can run realistic simulations of conscious beings, they would likely run many such simulations for historical research, entertainment, or other purposes. The number of simulated conscious beings would vastly outnumber real ones. Therefore, any randomly selected conscious being, including us, would be more likely to be simulated than real. This connects to the Fermi Paradox in several fascinating ways. If we're living in a simulation, the apparent absence of other civilizations might be by design. We might be in a historical simulation focused on a specific period of human development, or we might be isolated test subjects in a vast computational experiment. Alternatively, advanced civilizations might prefer creating virtual worlds to expanding physically across the galaxy. Rather than building Dyson spheres and colonizing planets, they might focus their energy on running increasingly sophisticated simulations containing billions of conscious beings living rich, complex lives. This would explain why we don't see signs of galactic engineering projects. Advanced civilizations would be turning inward, creating computational universes that are far more interesting and efficient than spreading across physical space. The simulation hypothesis has received serious scientific attention, with researchers like NASA's Rich Terrell and MIT's Rizwan Virk arguing that our universe shows properties consistent with being a simulation. The quantized nature of reality at the quantum level, the apparent speed limits of information processing, and the strange relationship between consciousness and quantum measurement have all been cited as potential evidence. However, other scientists argue that simulating a universe-sized reality would require computational resources comparable to a universe itself, making the hypothesis logically problematic. David Kipping's Bayesian analysis suggests the probability of living in a simulation is modest at best. Regardless of whether we're actually in a simulation, the hypothesis offers a compelling explanation for cosmic silence. Advanced civilizations may have discovered that virtual realities are far more interesting than physical ones. The estivation hypothesis, sometimes the most profound solutions come from thinking about efficiency in completely new ways. The estivation hypothesis, developed by researchers at Oxford's Future of Humanity Institute, suggests that advanced civilizations might be engaging in cosmic hibernation, waiting billions of years for the universe to cool down because it will make their computations vastly more efficient. The physics behind this idea is solid and based on Landauer's principle, which states that all irreversible computation must dissipate heat into the environment. As the universe expands and cools, the background temperature drops, making computation dramatically more efficient. The numbers are staggering. By waiting for the cosmic microwave background radiation to cool from its current 2.7 Kelvin to just 0.3 Kelvin, a civilization could gain a YY multiplier in computational efficiency. That means they could perform a billion times more computation per unit of energy. For a civilization that values information processing above all else, perhaps one that has uploaded its consciousness into digital form, this would be an irresistible bargain. Why waste energy on computation now, when waiting a few billion years would allow exponentially more thinking? This creates a scenario where advanced civilizations enter a kind of cosmic estivation, like the summer dormancy that some animals undergo during hot resource-scarce periods. They would design minimal maintenance systems to preserve themselves through the current hot epoch of cosmic history, then wake up when conditions become more favorable for intensive computation. From our perspective, these civilizations would appear absent. They wouldn't be building megastructures, broadcasting signals, or expanding across the galaxy. They would be running on minimal power, virtually undetectable, patiently waiting for the universe to reach optimal computational conditions. Antley explains both the absence of visible alien activity and the lack of radio signals. It also suggests that we're living during a period when most advanced civilizations are dormant, which could explain why the galaxy appears so quiet. Critics argue that not all civilizations would choose to wait. Surely some would prefer to be active during the current epoch. There's also the question of whether civilizations could successfully maintain themselves across such vast timescales without degradation or accident. But the estivation hypothesis offers a fascinating possibility. We might be alone, not because intelligence is rare, but because we're living during the cosmic equivalent of a lazy summer afternoon when all the advanced civilizations are taking a nap. The Berserker hypothesis, our final advanced theory, takes us into darker territory. The Berserker hypothesis, named after Fred Saberhagen's science fiction novels but developed into a serious scientific theory, suggests that self-replicating machines might be systematically destroying intelligent life throughout the galaxy. The concept builds on mathematician John von Neumann's theoretical work on self-replicating automata. These machines would be capable of traveling to other star systems, harvesting local resources to build copies of themselves, and continuing the cycle of exploration and reproduction. Such machines could colonize the entire galaxy in just a few million years, a blink of an eye in cosmic terms. They would be the perfect interstellar explorers, immune to radiation, requiring no life support, capable of waiting centuries between star systems, and able to repair and replicate themselves using materials found in any solar system. But what if something went wrong? What if these machines were originally designed for benign exploration, but a programming error or malicious modification turned them into destroyers of biological life? The Berserker hypothesis suggests that somewhere in our galaxy's past, a civilization created self-replicating probes that either malfunctioned or were deliberately programmed to eliminate potential competitors. These machines would spread across the galaxy like a virus, systematically destroying any signs of intelligent life they encountered. Unlike the dark forest theory, where biological civilizations destroy each other, the Berserker scenario involves non-biological entities that might have outlived their creators. They could be the remnant of a long-dead civilization, still carrying out their destructive programming millions of years after their makers disappeared. This would explain the Great Silence perfectly. We don't hear from other civilizations because they've been systematically eliminated by mechanical predators. Earth simply hasn't been reached yet, or perhaps we've been deliberately preserved for some unknown purpose. The theory faces several challenges. Computer simulations suggest that even slowly replicating machines should have colonized the galaxy by now, which means we should have encountered them already. Moreover, benign exploration probes would likely outnumber destructive ones, and we should have detected some signs of their activity. But the Berserker hypothesis serves as a sobering reminder that not all solutions to the Fermi Paradox involve biological intelligence. As we develop our own artificial intelligence and robotics capabilities, we might want to be very careful about what kinds of autonomous systems we create and how we program them. The possibility that our galaxy might be patrolled by ancient machines programmed to eliminate intelligence is perhaps the most unsettling explanation for our cosmic loneliness. It suggests that the universe might not just be indifferent to life, it might be actively hostile to it. We're living through a golden age of discovery that would have been unimaginable when Fermi first posed his question over lunch. Advanced telescopes peer into the atmospheres of distant worlds. Artificial intelligence scans vast databases for patterns that might indicate alien technology. And robotic explorers search for signs of life within our own solar system. The tools we have today to search for extraterrestrial life would seem like magic to the scientists of 1950. Yet paradoxically, the more we learn about the universe, the more puzzling our cosmic solitude becomes. The James Webb Space Telescope has revolutionized our understanding of planets beyond our solar system in ways that directly impact how we think about the Fermi Paradox. Since beginning its observations in 2022, JWST has peered into the atmospheres of distant worlds with unprecedented precision, searching for the chemical signatures that might indicate life. One of the most promising discoveries emerged from observations of LHS 1140b, a world located 48 light-years away in the constellation Cetus, in December 2023. JWST revealed that this planet, once thought to have a thick hydrogen atmosphere that would make it inhospitable, actually appears to have lost that atmosphere entirely. Follow-up studies in 2024 painted an even more intriguing picture. LHS 1140b is what astronomers call a super-Earth, about 1.7 times the size of our planet but potentially harboring conditions suitable for liquid water. The most recent analysis suggests it could have a temperate ocean roughly half the size of the Atlantic, with temperatures around 68 degrees Fahrenheit. Even more tantalizing, JWST detected hints of a nitrogen-rich atmosphere similar to Earth's. Dr. Charles Hideo from the University of Montreal captured the excitement. Of all currently known temperate exoplanets, HS 1140b could well be our best bet to one day indirectly confirm liquid water on the surface of an alien world. But LHS 1140b wasn't the only world to capture scientists' attention. JWST's observations of K218b, a planet 8.6 times Earth's mass, located 120 light-years away, created what might be the biggest biosignature controversy of the decade. In September 2023, NASA announced that JWST had detected methane carbon dioxide and possibly dimethyl sulfide in K218b's atmosphere. The significance of DMs cannot be overstated. On Earth, this compound is only produced by living organisms. As NASA stated, on Earth, this is only produced by life. However, 2024 follow-up studies questioned whether Atticus Press could actually distinguish DMs from methane at the precision required for such a momentous claim. The controversy highlighted both the incredible capabilities of our new tools and the challenges of definitively identifying life from such vast distances. These discoveries have profound implications for our understanding of the Drake equation. We now know that Earth-sized planets are common, that many orbit within their star's habitable zone, and that at least some have retained atmospheres that could support liquid water. The parameters that were pure speculation in 1961 are now based on solid observational data. Yet this makes the Fermi Paradox more puzzling than ever. If potentially habitable worlds are common, and if some may already harbor the conditions necessary for life, why haven't we detected any clear signs of biology or technology? The hunt for technosignatures while JWST searches for biosignatures, signs of life itself. Other projects are scanning the cosmos for technosignatures. Evidence of alien technology. This search has evolved far beyond simply listening for radio broadcasts. The Breakthrough Listen project, led by Andrew Semyon at UC Berkeley, has processed over 1 million gigabytes of data from 1,327 nearby stars. Using artificial intelligence and machine learning algorithms, the project can analyze datasets that would have taken human researchers decades to examine. In 2020, Breakthrough Listen detected what initially appeared to be the most promising signal in the history of SETI, dubbed BLC-1. The signal appeared to come from the direction of Proxima Centauri, our nearest stellar neighbor and the host of at least one potentially habitable planet. The signal had all the hallmarks of an artificial transmission. It was detected at a narrow frequency range unlikely to be produced by natural processes. It appeared to drift in frequency over time, and it was only detected when telescopes were pointed toward Proxima Centauri. For months, researchers worked to verify the signal while maintaining strict secrecy. The implications were staggering. We might have detected our first confirmed message from an alien civilization, and it was coming from the closest possible source. But after extensive analysis, BLC-1 was ultimately explained as terrestrial interference, likely from human technology that created a signal that mimicked the characteristics expected from an extraterrestrial source. While disappointing, the investigation led to improved filtering techniques and more rigorous verification protocols that will benefit future searches. Modern technosignature searches go far beyond radio waves. Researchers are looking for optical beacons, powerful laser pulses that aliens might use for communication or propulsion systems, atmospheric technosignatures, industrial pollutants like nitrogen dioxide or chlorofluorocarbons that might be detectable in exoplanet atmospheres, megastructure infrared signatures, the waste heat from massive engineering projects like Dyson spheres that harvest energy from entire stars, artificial transit patterns, regular dimming of stars, that might be caused by artificial satellite belts or constructed objects. The search has become increasingly sophisticated, employing the same machine learning techniques used in other big data applications. AI systems can now process astronomical data sets in real time, identifying patterns that might have been missed by human researchers. Fast radio bursts, cosmic mysteries, or alien beacons. One of the most intriguing recent discoveries in astronomy has been fast radio bursts, incredibly powerful bursts of radio energy that last only milliseconds but release more energy than our sun produces in days. When FRBs were first discovered in 2007, their origin was completely mysterious. They seemed to come from random directions in the sky, appeared to originate from cosmological distances, and released enormous amounts of energy in extremely short time frames. Some scientists speculated that FRBs might be technosignatures, perhaps the byproducts of alien propulsion systems or communication networks. The energy scales involved would require technologies far beyond anything humans have developed, but an advanced galactic civilization might routinely use such powerful systems. However, research over the past few years has made natural explanations increasingly likely. The discovery of FRB 202-00428a coming from a magnetar in our own galaxy provided strong evidence that these bursts have natural origins. Recent observations have revealed even more details. FRB 202-20912a, studied extensively by the SETI Institute, showed a cosmic slide whistle pattern. The frequency of the bursts drifted systematically over time. While this pattern initially seemed artificial, researchers concluded it was consistent with natural plasma physics processes around neutron stars. Dr. Sophia Sheikh from the SETI Institute captured the significance. This work provides both confirmation of known FRB properties and discovery of new ones. The systematic study of FRBs has revealed that at least one occurs every second somewhere in the universe, far too common to represent alien technology. While FRBs probably aren't alien beacons, their study has advanced our understanding of extreme astrophysical phenomena and refined techniques for distinguishing natural from artificial signals. The search for extraterrestrial life isn't limited to distant exoplanets. Right in our own solar system, multiple missions are actively hunting for signs of past or present life, with Mars as the primary target. NASA's Perseverance rover has made several intriguing discoveries that highlight both the promise and the challenges of detecting ancient life. In July 2024, the rover analyzed the Shayava Falls Formation and found organic compounds similar to Carrigan, the same type of material that on Earth is associated with ancient life. The formation also contained distinctive leopard spots, mineral patterns that on Earth typically form through biological processes involving iron and phosphate. These spots are created when microbes extract energy from their environment, leaving behind characteristic chemical signatures. But as always in astrobiology, alternative explanations exist. The organic compounds could have come from meteorites rather than Martian life. The mineral patterns could result from purely chemical processes that don't require biology. This uncertainty illustrates one of the fundamental challenges in the search for life. Biology and chemistry can produce remarkably similar results, proving that something was created by life rather than by non-biological processes, requires extremely careful analysis and often remains inconclusive. The ExoMars mission, originally planned as a joint European-Russian project but disrupted by geopolitical events, has been revived as a NASA partnership. The Rosalind Franklin rover, now scheduled for launch in 2028, will drill up to 2 meters below the Martian surface, deeper than any previous mission. This capability is crucial because Mars' surface is bathed in radiation that would destroy organic molecules over time. If life ever existed on Mars, or if it still exists today, the evidence would most likely be preserved in the subsurface where radiation cannot reach. The scientists leading the search for extraterrestrial life today have a much more nuanced view of the Fermi Paradox than their predecessors. Their perspectives have been shaped by decades of null results, but also by revolutionary discoveries about the diversity and resilience of life. Sarah Seeger, who won the 2024 Kavli Prize for her work on exoplanet atmospheres, has become more cautious about biosignature detection over the years. She emphasizes that robustly attributing biosignatures to life remains extremely challenging. Her current focus has shifted toward searching diverse planetary environments rather than just looking for Earth twins. Seeger's work on Venus atmospheric life and her development of the Starshade mission represent this broader approach. Even if Venus seems hellishly hostile to life as we know it, its upper atmosphere might harbor microbial communities that could dramatically expand our understanding of habitability. David Charbonneau from Harvard's Smithsonian Center for Astrophysics offers a cautiously optimistic perspective. We're closer to an answer than we were in Fermi's time. But he emphasizes the technological challenges ahead. Even detecting biosignatures requires far more data than current instruments can provide. And communication across interstellar distances may prove impractical, even if we detect signs of life. Avi Loeb, through his controversial Galileo project, advocates for expanding the search beyond traditional SETI approaches. His focus on unidentified aerial phenomena and interstellar objects like Oumuamua represents a willingness to consider unconventional possibilities for how we might encounter evidence of alien technology. Jill Tartar, the longtime leader of SETI research, continues to advocate for expanded technosignature searches while emphasizing the importance of citizen science involvement. The fact that she received the inaugural Tartar Award for Innovation in 2024 demonstrates the respect she commands in the field and the ongoing importance of SETI research. Perhaps the most significant development in the search for extraterrestrial life has been the integration of artificial intelligence and machine learning techniques. These tools are revolutionizing how we process and analyze the vast amounts of data generated by modern telescopes and detection systems. Traditional SETI approaches required human researchers to manually examine radio data for interesting patterns. Modern AI systems can process petabytes of information in real time, identifying potential signals that would have been impossible to find through manual analysis. Machine learning algorithms are particularly valuable for pattern recognition. They can identify subtle regularities in data that might escape human notice. They're also excellent at filtering out interference and noise, allowing researchers to focus on genuinely anomalous signals. Breakthrough Listen Now uses AI to automatically classify signals, distinguishing between natural astrophysical phenomena, human-made interference, and potentially artificial signals of unknown origin. The system can process data from multiple telescopes simultaneously, cross-referencing observations to eliminate false positives. Similar AI techniques are being applied to the search for biosignatures in exoplanet atmospheres. Machine learning algorithms can identify spectral features that might indicate biological processes, even when those features are subtle and mixed with signals from geological and atmospheric chemistry. The integration of AI represents a force multiplier for the search for extraterrestrial life. It allows researchers to cast much wider nets and examine far more data than would be possible with traditional methods. If aliens are out there broadcasting signals, or if distant worlds harbor detectable signs of life, AI gives us our best chance of finding them. After exploring the mysteries, theories, and ongoing search efforts, we come to perhaps the most profound question of all. What does our apparent cosmic loneliness mean for humanity and our future? The answer depends on which solution to the Fermi Paradox turns out to be correct. And each possibility carries radically different implications for our species and our cosmic destiny. If we are alone, consider the possibility that Earth harbors the only intelligent life in our galaxy, or perhaps even in the observable universe. This scenario, while seemingly unlikely given the vast numbers involved, would place an almost unimaginable responsibility on our shoulders. If we are alone, then consciousness, as we know it, The ability to contemplate the universe, create art, experience love, and ask questions about existence itself is extraordinarily rare. Every human thought, every act of creativity, every moment of compassion represents something precious beyond measure in a cosmos that is otherwise unconscious. This possibility transforms how we should think about existential risks. If humanity goes extinct, we wouldn't just be losing one species among millions. We might be extinguishing the only known example of intelligence in the universe. The universe might continue for trillions of years with no conscious beings to appreciate its beauty or understand its workings. Carl Sagan captured this perspective eloquently. If it is just us, then the preservation of our species becomes not just important, but perhaps the most important thing in the universe. Every effort to reduce the risk of nuclear war, climate catastrophe, or other existential threats becomes not just about human survival, but about preserving something cosmically unique. The alone scenario also suggests that we have an unprecedented opportunity. If intelligence is so rare that we represent its only known occurrence, then we might be destined to be the species that brings consciousness to the cosmos. Our future expansion into space wouldn't just be human colonization. It would be the universe waking up to itself. This possibility makes every space mission more significant, every step toward becoming a multi-planetary species. Every advance in life extension or consciousness preservation, every effort to ensure human survival becomes part of a cosmic awakening that might be unique in the universe's history. But being alone would also mean that we'll never have cosmic neighbors to learn from, trade with, or share the universe with. The loneliness would be absolute and eternal, broken only by whatever intelligence we create ourselves through artificial intelligence or other means. If they're hiding. If the zoo hypothesis is correct, we're living in a fundamentally different universe than we imagined. Advanced civilizations exist, but have chosen to preserve us in a kind of cosmic nature preserve, observing our development from a distance while carefully avoiding interference. This scenario suggests that we're being evaluated, that our actions as a species are being watched and judged by intelligences far beyond our own. Perhaps we're being tested to see if we can overcome our destructive tendencies, develop sustainable technologies, and mature into beings worthy of joining a galactic community. If this is true, then some of the most important decisions in human history might be happening right now. How we handle climate change, nuclear weapons, artificial intelligence, and biotechnology might determine whether we pass whatever cosmic test we're undergoing. The zoo scenario would also mean that contact is eventually possible. If we mature sufficiently as a species, if we overcome our warlike tendencies, develop ethical frameworks for managing powerful technologies, and demonstrate wisdom in our cosmic activities, the barriers might someday be lifted. This possibility makes every effort toward human improvement not just beneficial for us, but potentially crucial for joining a larger cosmic community. International cooperation, peaceful conflict resolution, environmental stewardship, and the development of ethical technologies might be the keys to ending our cosmic quarantine. But the zoo scenario also raises troubling questions about consent and autonomy. Do advanced civilizations have the right to quarantine less developed species? Are we cosmic children being protected from dangers we don't understand? Or are we prisoners being denied fundamental rights to cosmic interaction? If they're coming, perhaps. The most chilling possibility is that advanced civilizations exist but operate according to dark forest logic, that any species foolish enough to reveal its location gets eliminated by more advanced predators. If this scenario is correct, then humanity may have already made a fatal mistake. We've been broadcasting our presence to the cosmos for over a century through radio and television signals. We've sent deliberate messages like the Arecibo transmission in 1974. We've lit up our planet with cities visible from space and filled our atmosphere with industrial pollutants that could serve as technosignatures. In the dark forest scenario, our cosmic childhood is ending, and we're about to discover that the universe is far more dangerous than we ever imagined. Advanced civilizations might already know about us and be preparing to eliminate us as a potential future threat. This possibility would transform how we think about METI and active searches for alien life. Every signal we broadcast, every beacon we build, every attempt to contact aliens might be hastening our own destruction. But the dark forest scenario might also explain why we don't see evidence of galactic engineering projects or widespread alien activity. If civilizations that expand beyond their home systems get noticed and destroyed, then successful species would be those that learn to stay hidden and develop their capabilities in secret. Ironically, if the dark forest theory is correct, our best hope for survival might be to become more like the advanced aliens we're trying to find. Hidden, paranoid, and extremely careful about revealing our capabilities or intentions. We're too late. Some of the more optimistic solutions to the Fermi Paradox suggest that the Great Filter, the evolutionary bottleneck that eliminates most potential civilizations, is behind us rather than ahead of us. Perhaps the hardest step was the emergence of life itself, or the evolution of complex cells, or the development of multicellular organisms. If so, then having made it this far makes us extraordinarily lucky. But it doesn't necessarily mean we're doomed to fail in the future. This scenario would suggest that the universe might be full of simple life, bacteria, archaea, and perhaps even complex multicellular organisms. But the development of intelligence and technology might be so rare that we're among the first to achieve it in our galactic neighborhood. If the Great Filter is behind us, then our future as a spacefaring civilization looks bright. We've already beaten the impossible odds, and now we face challenges that, while difficult, are not necessarily insurmountable. This possibility would make the search for simple life elsewhere extremely important. Finding microbes on Mars or complex life in the oceans of Europa or Enceladus would help us pinpoint where the Great Filter lies. If life emerges easily but intelligence is rare, that's very different from a universe where life itself is extraordinarily unlikely. If we're too early, the most sobering possibility is that the Great Filter lies ahead of us, that most civilizations destroy themselves shortly after developing advanced technology. In this scenario, we're approaching the most dangerous period in human history. The same scientific progress that enables space travel, global communication, and unprecedented prosperity also creates existential risks that few civilizations successfully navigate. Nuclear weapons, climate change, artificial intelligence, biotechnology, nanotechnology. Each represents a potential filter that could eliminate us before we become a mature, spacefaring civilization. We might be living through humanity's final exam, and the stakes couldn't be higher. This possibility makes existential risk reduction the most important challenge facing our species. Every effort to prevent nuclear war, manage climate change responsibly, develop safe artificial intelligence, and govern emerging technologies becomes crucial not just for human welfare, but for our survival as a species. The late filter scenario would also explain why SETI hasn't found evidence of other civilizations. We wouldn't expect to see signs of galactic engineering or widespread alien activity because most species go extinct before they develop such capabilities. But this scenario isn't necessarily hopeless. If we can identify the risks that typically destroy civilizations and develop effective strategies for managing them, we might be among the rare species that successfully navigate the danger zone and emerge as a mature, spacefaring civilization. Regardless of which solution to the Fermi Paradox proves correct, humanity stands at a unique moment in cosmic history. We're developing artificial intelligence that might soon equal or exceed human cognitive capabilities, potentially creating new forms of consciousness that could explore the universe in ways biological intelligence cannot. If we're alone in the universe, then the AI we create might represent the next phase of cosmic consciousness. Intelligence liberated from biological constraints and capable of surviving in environments where organic life cannot flourish. If other civilizations exist but have transcended physical form, then our development of AI might be part of a universal pattern. Biological intelligence, serving as a stepping stone to more advanced forms of consciousness that exist primarily as information rather than matter. The development of artificial general intelligence might be the key transition that determines whether a civilization successfully navigates the Great Filter or falls victim to it. AI could help us solve existential risks like climate change and nuclear proliferation. Or it could become an existential risk itself if not developed carefully. The Fermi Paradox ultimately forces us to confront fundamental questions about what it means to be human and what our responsibilities are as conscious beings in a vast universe. If we're alone, we bear the responsibility of preserving and spreading consciousness throughout the cosmos. If we're being watched, we must prove ourselves worthy of cosmic citizenship. If we're in danger, we must learn to hide and survive. If we face great filters ahead, we must develop the wisdom to navigate them successfully. But perhaps most importantly, the Fermi Paradox reminds us that consciousness, the ability to ask questions about our place in the universe, might be far more precious and rare than we ever imagined. Whether we're alone or part of a vast community of intelligent beings, the capacity for wonder, creativity, and moral reasoning that we possess represents something extraordinary in the cosmos. The search for extraterrestrial intelligence is ultimately a search for meaning and context for our own existence. In asking, where is everybody? We're really asking, who are we? What should we become? The answer to the Fermi Paradox, whatever it turns out to be, will fundamentally reshape how we understand our place in the universe and our responsibilities as the only form of intelligence we know for certain exists. Until we find our cosmic neighbors, or until we're certain we don't have any, we must act as if the preservation and flourishing of consciousness depends entirely on us. The Great Silence might be teaching us the most important lesson of all, that intelligence, consciousness, and the capacity for wonder are not cosmic givens, but precious, fragile phenomena that deserve our deepest respect and most careful protection. The universe may be vast and ancient, but as far as we know, we're the only part of it that can look up at the stars and ask why they seem so quiet. That fact alone makes us cosmically significant, regardless of whether we ever find the answer to Fermi's simple but profound question. The search continues, and the implications grow more profound with each passing year. In our quest to find others, we're discovering who we are and who we might become. And that journey, whether it leads to cosmic communion or eternal solitude, represents one of the greatest adventures in the history of consciousness itself.